Very, very much for the occasion. Also, for those who weren't here last year, I had some conjectures which we had to revise. So I'll tell you the story. For some of you it may a little bit overlap, but possibly not. So anyhow, here is the difficulty of counting. Not everybody seems to realize why counting is difficult. And now this is joint work with Tomer Kotek, Mickey Herman, Steve Noble, Andrew Goodall, and Lena Rave. Kotek and Rave were my former students. And we have just two papers which just were now accepted in revised form. So
I think Andrew Goodall's photo is actually in this room.
What?
The photo of Andrew Goodall
is in this room?
Yeah, probably.
Why, there are many rooms with wood and
Oh, this looks identical. I mean, he was here. Actually.
Ah, he was here? Yeah, maybe this is the photo. Okay. And okay, so it's partially done at the Simons Institute, and also there are some additional remarks who originate from my new graduate student Rakita. So the outline is like this. I will tell you something about Harari polynomials, then I will tell you something about complexity of computing and the complexity of univariate polynomials. Oops, something is wrong here. It goes in the other direction. Anyhow, so we start with the complexity of the chromatic polynomial. Now the chromatic polynomial is a very old object. It was, depending whether you are a die-hard Platonist or not, invented, found, discovered, defined by Birkhoff. Actually, in his case, it was defined, but then it was found to be a polynomial. And he looked at a graph parameter chi of a graph and an integer, positive integer k, which was supposed to count the number of proper colorings in the traditional sense of the four-color conjecture of a graph with k, with at most k colors. And so this is a coloring of the vertices such that two neighboring vertices get different colors. And Birkhoff noticed that this graph parameter with integer values happens to be a polynomial in K. And furthermore, he noticed also, this is follows from the definition, that for edgeless graphs with n vertices, it happens to be K to the n. And if you delete or contract edges, you get a recurrence formula, and then you can use these two facts to show that by induction that this is a polynomial in K. And once you know it's a polynomial in K, it can be extended to any ring which contains the integers, and then we denote it by chi of gx. And you can also ask if there is a combinatorial meaning if you evaluate it at -1, at square root of 2, at pi. But it is a graph parameter, meaning that is for two isomorphic graphs, it gives you the same value, even if you don't know why you want to know the number of colorings with pi many colors. Now, when you want to compute this, counting the number with 0 colors is trivial, with 1 color is also trivial, and with 2 colors it can be computed in polynomial time, and with 3 colors at most it is Sharpe complete in the sense of Valiant's hierarchy of counting complexity, and for -1 and for 4 and for 5 and 6 it is Sharpe complete. It was shown by Natilineal. And then you wonder how, if you take now, let's be modest first, if you take a rational number Even if it doesn't have a meaning, it's a well-defined graph parameter. How difficult is it to compute for 1/2, 1/3, or even for a complex number which is not a rational number? Now there is a trick which was noted by Nattilineal, that if we denote by this bow tie the join of two graphs, so disjoint union, and you connect everybody from one side with everybody from the other side. And if you add to a graph a clique by joining it, and then this is the same, and you compute for lambda the number of colorings, then this is the same as computing it for G for lambda minus n, and with a correcting factor, lambda to the falling factorial of n, and hence we get that for 4 is the same as 4 times for 3, and in general you get a reduction formula like this, and therefore for every integer bigger than 3, computing the polynomial is still Sharpe complete. Now, as a matter of fact, you get a dichotomy theorem here. It's like in classical mathematics, even if you don't know whether the continuum hypothesis is true, for certain classes of sets, it's either countable or continuum or whatever. So here, for certain evaluations, it's either polynomial time computable or it is Sharpe hard, and nothing in between happens. Unless there is nothing in between. Okay. So we call this situation that you have so you have a graph polynomial, any graph parameter which is parameterized, and you look for which parameters is hard, and it is easy. So in this case we speak of a difficult point dichotomy, that for most of the points it's as hard as possible, and for a few points it is easy and nothing is in between. So this is the situation for the chromatic polynomial, and we're going to see a few more polynomials, and we'll ask a similar question. So there is a subtle problem here when you want to evaluate the complexity of the chromatic polynomial at pi. What is your computational model? And if you compute it over the rational numbers, then you can say, okay, the rationals are pairs of integers. We can use the Turing model, so this is meaningful. But otherwise, we don't know where we are. So we can say it's hard if it is somehow reducible to something which is hard in the Turing model, even if the problem itself doesn't sit in the Turing model properly. So this is what people do in the literature, but in some sense this is not very satisfactory, but I'm not going to spend too much time discussing this. I have a different talk. I can give you a link about this problem. Anyhow, there is an alternative for this situation. Actually, Martin Ziegler did hear my talk about the other problem. So there is a notion p time over the reals, or Sharpe over the reals, where you use the Bloom-Schub, I don't like the name Bloom-Schub-Smale because it was invented 20 years before, or by Shepardson, but and other people. But anyhow, they added a touch of complexity which wasn't there before. So there is a computational model which is called Bloom-Schub-Smale model, and the book is written together with Philippe Zucker on top of it, and they defined polynomial time over the reals and NP over the reals, and Klaus Mayer defined Sharpe over the reals. And you can also look at this situation, but Sharpe over the reals behaves unexpectedly differently, and we don't actually understand it properly. So, but this is maybe the better way of looking at this. And then there is a combination of Bloom-Schub-Smale with finite model theory, which is called metafinite model theory, which was invented by Erich Kreider and Yuri Gurevich. And we had months ago a workshop at LIX reviving the topic, but it's not a very active field of research, but there are very interesting problems there. So there are some facts which I skip now, but here we can see now what is the situation about a chromatic polynomial. So if you evaluate it at alpha 1, 0, 2, in the Turing model this is all in P, and if you take any field or the reals or the complex, then it is also in P. If you take any integer different from 0, 1, 2, in the Turing model this is sharp P, and in BSS you cannot say this. You can only say this in exponential time over the field or over the reals. And in the complex number, strange enough, it does fit. It does fit the sharp P definition of Klaus-Mayer. And if you take any A which is different from a positive integer, then for the Turing model it is not clearly defined, and for BSS you only get upper bounds which are not very good. And lower bounds is similar, so the whole point I want to say is that if you study this complexity, you have to be a bit more careful and make precise what you mean in situation where I marked it here as undefined.
So it's sharp P means sharp P complete, right? So the X.
No, it's in sharp P.
In sharp P. So you don't.
And the lower bounds. No, if it is upper bound and lower bound sharp P, then it is sharp P complete. But then the table doesn't show completeness in the other cases. Okay. So yes, in the Turing model, when it is defined, then it is sharp P complete. But in some cases it's not defined, and in the other cases you only have upper bounds and lower bounds, which don't fit. So anyhow, I want to say that this is an unsatisfactory situation, and there is a lot of work to do, but we won't have time enough. If I leave you the slides, there is a sequence of slides here, which allows you to look at this more closely, but we can go now to this. So now, no, there is something is wrong here. Somehow my link don't function. Okay, here. Okay, here. So we look at something which is it was defined by Harari, but it's actually a naive definition. We look at a chromatic polynomial as a coloring, but instead of, so what do we require? That every set of points which has the same color induces a subgraph which has no edges. This is the same as saying it's a proper coloring. And no two points have an edge if they have the same color, so the induced subgraph has no edges. So now we can look at, now you fix your favorite graph property. What is your favorite graph property? Planar, okay. So you can say now, let's look at a map. We color the vertices, and we require that the set of vertices which get the same color induces a planar graph. What's wrong with this definition? So we call this a planar coloring. If you don't like planar graphs, you take triangle-free graphs, and then you require that color class induces a triangle-free graph. And somebody else wants a Hamiltonian graph, and then, okay, he can have this also. So actually for every graph property, whether definable in some logic or not, or complexity or not, just a graph property, a family of graphs closed under isomorphism, P, we can introduce a P coloring. And okay, so Harari wrote a paper about P colorings. Now once you have defined P colorings, you can do two things. You can try to do extremal graph theory, or you can count. And in the literature, the extremograph theory happens. I mean, many of those for certain properties, there are a series of papers or many papers or at least one paper where somebody discusses some extremograph property. If the edges are like this, then at least it can be done with that many colors or something like this. Now, when I started to work on graph polynomials, I found out with Boris Silber, or actually Boris Silber suggested an idea and then we worked it out, that for every graph G, the counting of p-colorings is a polynomial in K. However, the proof is not like Birkhoff's proof is deletion and contraction, but it's a straight counting argument. I mean, Silber had a very deep model theoretic reason why he thought it, but this is the first way he saw it, and when we analyzed the proof, we could kick out quite a bit of his model theory, at least for the cases here, and we could prove that that for every p, the number of Harari p colorings with at most k colors is a polynomial in K. So now all of a sudden you have many graph polynomials, but you don't know what to do with them. See, in the chromatic case, I have slides, but I won't show you today. But in the chromatic case, Birkhoff really wanted to prove the four-color conjecture using analytic methods. And there are plenty of results, and 2 days ago you heard Johann talking about, and he has a corollary to the theory explained 2 days ago, but he didn't talk about it 2 days ago, is that people were looking at a chromatic polynomial and they looked at the coefficients of the polynomial in the standard presentation, or the absolute values of the coefficients in the standard presentation, and Welsh and other people conjectured 60 years ago that this sequence is unimodal, and it resisted proofs, and it follows from John's work that indeed it is unimodal. But he doesn't care about unimodality. This was a good point to show that his new theory has very dramatic and unexpected applications. But I asked him also, he doesn't really, didn't know why the question would be or would not be interesting or something. It's just a proof that his fantastic new methods have unexpected applications. But so here you have now many graph polynomials, and you can ask all those questions as well. What is the complexity? What can be done? What is it? So let's have a look at those.
So you don't require any conditions on P, like hereditary or something? So
no, just to be a property, just closed under isomorphism.
Closed under isomorphism.
We'll see if you get hereditary, and there will be. So here is a general question, and I'm not sure it's a deep question in the sense, here I define something. Now the natural question for a mathematician is there anything intelligent you can say about a new situation? And before you can decide whether it is interesting or not, you have to collect a couple of statements which somehow look intelligent and non-trivial, which you can say about the situation, and then you start to see whether it develops into something. But at the moment, instead of one chromatic polynomial, I have all of a sudden uncountably many graph polynomials, and it's not clear what we want to do with them. So we just want to see, is there anything it has in common with others? So here comes your multiplicativity. A graph polynomial is multiplicative with respect to disjoint union, but again you can have, instead of disjoint union, any other graph operation if you want, but disjoint union is what is allowed if it is multiplicative. You compute the graph polynomial on a disjoint union, then it's the same as the product of the factors. And then indeed, if a graph polynomial is hereditary, if all it's closed under induced subgraphs, and it's additive if it is closed under disjoint unions. And proposition, which is not difficult, but one has to observe it, and then still it takes 2 pages of proof or 3 pages of proof. Assume a graph property is hereditary and additive, then the Harari polynomial for P is indeed multiplicative. So here is a situation which answers your question, which is not very deep, but at least it shows something. Now the chromatic polynomial, the classical, has this property that we can look at deletion of graphs and contraction of graphs, and we get, so deletion is what you think it is, you take the edge away, and contraction is that you identify the two vertices of the edge, and depending if you would look at simple graphs, then you throw away if you get a loop, and if you don't look at simple graphs, then you keep the loop, and so in the case of the chromatic polynomial, you throw away the loop, and you have this property. So here we keep the loop, and we say a polynomial is a chromatic invariant or a Tat-Grothendieck invariant if it behaves like this. There are polynomials in the corresponding many variables, alpha, beta, gamma, lambda, and mu, 5 of them. So we get a polynomial in 5 variables, such that the polynomial of G can be computed like this. If G has no edges, then you just take alpha to the number of vertices. If it is a loop, you take beta times the deletion of the edge. If it is a bridge, you take gamma times the contraction of the corresponding edge, and otherwise you take lambda of the deletion plus mu of the contraction. And it turns out that the Tat polynomial has this property, and the chromatic polynomial has this property. And okay, we also need a definition here. In the sequel, we say two graphs are similar if they are non-isomorphic, then not in a trivial way. So the graph theorists have a feeling that if two graphs have a different number of vertices, then the isomorphism problem is not interesting. So they are trivially non-isomorphic. The same is the number of edges, and the same is the number of connected components. You could add other ones, but this is the traditional set. And we say two graphs are similar if they have the same number of vertices, edges, and connected components. We'll need this in a moment. So we want to actually compare two graph polynomials. Now we have many, yes. So it makes sense to compare two of them, and to fit the literature from a logical point of view or from a purely analytic point of view. You could have different definitions, but we look at the distinctive power of a graph polynomial on similar graphs. And the reason is because in the literature this is how it is done, so we'll see in a moment. So two graphs are similar, what I said before, and two graph parameters, f, g, could be polynomials, could be numbers, could be something, are comparable. So f is at least as distinctive as g. If whenever g distinguishes and doesn't distinguish, then also f doesn't distinguish. And they are equivalent if they distinguish the same number of similar graphs, and then we say they have the same distinctive power. Now the graph theorists say they indeed use this notion implicitly. They would say the Tat polynomial is stronger than the chromatic polynomial, because indeed the Tat polynomial distinguishes more graphs than the chromatic polynomial, and it's only true for similar graphs, because otherwise somehow the number of connected components starts to play a role or whatever, so one has to be careful. So this is when in the literature somebody defines a new graph polynomial and says, hurrah, mine is better than yours, he would usually argue that why is it better than yours? Because it distinguishes more graphs. Now Brylavsky ages ago proved a theorem which says there is a chromatic invariant in the sense I defined before, u in 5 variables, such that we have the following statement. He didn't formulate it like this, but this is why I introduced this notion, such that for every other chromatic invariant f, we have that f is less distinctive than u. And the Tat polynomial is actually equally distinctive as u. Now here the similarity is very important because the U and the Tat polynomial behave differently on number of connected components on something, but if the graphs are similar, they are really the same. So we say two graphs are T equivalent, Tat equivalent, if they if they are not distinguished by the Tat polynomial. And then you wonder how strong the Tat polynomial is. And Brylovsky also showed that there are infinitely many pairs of non-isomorphic similar graphs G1 and G2, which are T equivalent. And Bolobash and Peabody and Riordan added a result which said that they can also be as connected as you want. And actually there is a very interesting open conjecture. So this shows that Tat polynomial is not a best possible graph invariant because there are isomorphic graphs, which non-isomorphic graphs which cannot be distinguished. But they ask whether almost all graphs are Tat unique. So is it true that the number of graphs which are the only ones for the Tat polynomial divided by the number of all of the graphs goes to 1 with n going to infinity? And this is a challenging open problem. So the Tat polynomial here, you don't have to know what is the Tat polynomial. It's just information I gave you is enough for understanding what I do. So here now you can ask a simple question. Is any of my new graph polynomials also chromatic invariant? No? So we looked at this, and it took us a little bit of work, but there are infinitely many first-order properties P such that the corresponding Harari polynomial is not a chromatic invariant. So infinitely often the answer is no. And there are infinitely many first-order properties P such that the graph polynomials are mutually, this should be STP. I somehow got the wrong version of the I have two PDF files. I somehow picked the wrong version. Are mutually STP incomparable. However, in 1, P is not explicitly given, and in 2, P contains up to isomorphism just a single structure. So here is this just shows that in many cases it's no, but we don't really know the full answer. So now we can also look at H-free graphs which have no induced subgraph isomorphic to H, and we denote by fr H the class of H-free graphs, and we look at the generalized chromatic polynomial when we take for P, for the Harari property, the H-free graphs, and then the student Rakita showed if H is connected, then this polynomial is again multiplicative, and if H is not a complete graph, then the corresponding key is not a chromatic invariant, so this is more explicit than what we had. And then there are infinitely many pairs of graphs H and H prime, such that key of these H-free graphs are not comparable. So we get many such polynomials which are not comparable. So here are some open problems, many, but here is one which I find interesting. Which graph polynomials are chromatic invariants? Can you? Now here is a simple question. You pick your favorite property P. You look at the Harari polynomial and you say, no, maybe it's a special case of the Tat polynomial. I mean, this would follow from Brylovsky's theorem, or maybe not. So, can you say anything about P which implies that it is a chromatic invariant? Well, we know if P is the H-free graphs, then it is a chromatic invariant. Is the chromatic polynomial the only graph polynomial which is a chromatic invariant? Conceivable. I didn't think long enough about this, say I conjecture. Maybe there are some trivial cases if you... I didn't think too much about it. But I mean, can you characterize the cases when it turns out to be a chromatic invariant? And are infinitely many graph polynomials which are mutually ST incomparable? So here the answer actually is yes, we proved this. Indeed I got the wrong set of slides. But this we solved in the meantime.
So for classes of graphs that are closed under minors, does this follow from the similar relativity theorem?
What's the question? Assume P is minor closed.
Right.
Fine. So then what?
The question what the
Whether it implies that it is a chromatic invariant?
with the question.
Go ahead, write a paper. I don't know. I didn't spend enough. I mean, this is rather recent. Just I was traveling now for a month where I had other things to do, and but a month ago I stopped thinking about this in particular. So I don't even know whether it is difficult or I just should sit down and. But yes, obviously, it's one of the first things you would try. Okay. So, yeah, there are many things. I think it's a good problem. It's a good thing to, but I don't think every progress you make is publishable. I mean, I've become the world expert on graph polynomials. Every month I get at least one paper to referee. And sometimes it's embarrassing because people take a polynomial like this and then they compute it for circles and paths and two other minor observations, and they write a 20-page paper and they want it published in the Discrete and Applied Mathematics or something, and it becomes embarrassing because it lacks a story. I mean, it's the kind of homework we used to do when we were students, when we had a seminar about this, not when we try to publish papers. So yes, you should sit down and play with it, but you shouldn't think for every intelligent observation you should already publish a paper. I think it's polluting the publication universe. Anyhow, but here is a question I'm guilty of. I conjectured in writing that actually this phenomenon of the dichotomy property we discussed before about the complexity is a universal phenomenon. And I have a huge list where it happens to be true for the Tat polynomial, for partition functions, for and so on. So the examples I had on my desk were all saying that, you know, there is a dichotomy property like this, and some of them were hard proofs, especially for Hollands or for special partition functions and so on. So I stupidly or maybe naively or maybe precautiously conjectured rather than ask the question that this phenomenon is universally true. Like Borel sets are continuum or not. But anyhow, so at some point we were collecting cases and we went to the Harari polynomials. We said, you know, you want to check your conjecture. So here is a way to, instead of starting with multivariate polynomials and Tat polynomials and partition functions and Hollands, where they all proved it, let's see for how many of those Harari polynomials the difficult point dichotomy holds. So here is a report of what we learned, and as you can hear from the way I explain, it was a sobering experience. Okay. So we look at the complexity spectrum of a univariate graph polynomial. So now you take your graph polynomial and you decide that you do it, say, over the reals. You fix your field, your ring or your field where you want to do it, but for the sake of the discussion, let's take the real numbers. And we look at the unigraph polynomial Q, univariate, and we say the easy points maybe I should have taken the other. I'm upset now. No, because I corrected all those misprints and I picked the wrong PDF file. But never mind. So forgive me. I will send you the corrected version. It is already corrected. Anyhow, easy P is P and Q is the same. So easy P here is the set of points, say in the complex numbers, such that evaluating the polynomial at A is doable in polynomial time. And for a graph polynomial Q, we look at the relation A is polynomial reducible to B for evaluations at A and B if the corresponding thing happens. And hard is where this is at certain point it is sharp P hard because it's a point which is well defined to be in sharp P, and every other point is more difficult than this. Okay. So avoiding the issue in which computational model this is, I give a definition which says there is a point which has an interpretation as being in sharp P, and we look at all the points which are harder than those. For which graph polynomials do we have such a dichotomy?
So I'm confused with hard. So hard is collection of A's, so that Q of A0 is sharply hard?
No, hard P is the set of evaluations at A such that there is a point there is a point A0 which is hard, and hard are all the points which are more difficult than the one at A0. So in the case of the chromatic polynomial, A0 would be 3. And the hard points are all those points which are more difficult. I mean, you can show the reducibility, but you don't know whether it happens to be in the... So, but the A0 is a hard point, and it's kind of the easiest hard point, and everybody else is...
So everybody else is also already sharply complete?
No, because it may be not in sharp P. Evaluating at pi or evaluating... It's only sharp P hard. But it's an abuse of notation because it's reducible to a point which is sharp P hard. It's not even sharp P hard. You don't know where it lives. But it's reducible. Okay, and then this defines what I spoke before with some people here. This defines also some I don't know, lattice of partial order, and you can look at the structure of this partial order of complexity. So there are polynomials which are always easy. For instance, the characteristic polynomial, which is defined to be a determinant of the adjacency, the characteristic polynomial of the adjacency matrix, and instead of the adjacency matrix, you can take the Laplacian, and again you use the characteristic polynomial. So for a very long, the characteristic polynomial was my adjacency matrix. Now recently, they look also at other variants of this, but obviously any graph polynomial which is defined by some determinant is easy to compute. If you take Chi, the property connected, what does it mean? That every color class induces a connected graph. No, the other way around. Every connected component has the same color. This is the other way around. It's difficult. Anyhow, this is also easy. You just have to analyze how many connected components you have, and then you see. So this gives SDPP is a strong version of the dichotomy property. Now here is the first sobering surprise. I gave talks at Dachstuhl where I casually said, the edge colorings where no two edges who meet have the same color is a graph polynomial. Obviously, you don't need our heavy theorem for this, because the line graphs are special cases, and then I thought the complexity should be the same. So anyhow, we look at edge colorings, and we observe indeed edge coloring is a proper coloring of a line graph. So therefore, the number of proper edge colorings with at most k colors is a polynomial in K. this was all well known, and then people didn't think it is interesting. Now, the situation here is rather surprising. The complexity of counting the number of edge colorings turned out to be non-existent in the literature till 2014. Although Valiant defined all these counting problems already in the 80s. And in a rather difficult paper by Tsai, Guo, and Williams, they proved the following: Sharpie edge colorings, counting the number of edge colorings, is Sharpie hard over planar regular graphs for all anyhow. So for us it is hard for most of the cases, and it's trivially tractable if K doesn't satisfy this inequality. And the proof is really very, very complicated, and it only works for integer value of positive integers. So they got a complete analysis in the cases where K really means colors. but the trick of linear, that you can have a reduction, that if you know how to do 4, then you can also do 3, or when you know how to do pi, you can do 3. Doesn't work here. So there are actually two problems here. One is to do this maybe with a more elementary proof, and two, to extend the analysis to points which are not positive integers. Now the first one, finding a simple proof, Tsai didn't like it. He thought this is he was happy, but it's a 60-page paper. but they do more than this. But they introduce Hollands and all kind of I mean, can you do a proof which you can do in an undergraduate seminar in reasonable time? This is what I have in mind when I mean simpler proof. Anyhow, so this is wide open. We couldn't find it, and I was very embarrassed because this happened in Dutch too. I didn't lecture it, but just before I started to lecture, I went through. I had a slide which says trivially this also holds for edge colorings, and then I all of a sudden realized that my proof was wrong, and then I checked the literature and I found out about this. So in general, when you want to do analysis of this, there are two problems. First of all, you have to find at least one evaluation point where you can show it is difficult. And the second one is then you have to use it somehow to be able to move it around, which we call linear trick, but it's just some form of algebraic reduction. So now let's go to another case. And this is what I'm telling you is now something what you would do in a seminar. You present a question, and then before you continue, you say, look, I checked a few examples, and let's see what happens. So here is the next example. I checked the coloring is convex with K colors if every monochromatic set of vertices induces a connected graph. This is what I wrongly said before. So before it was if every connected component has the same color. So here it's the other way around. You look at, so if you look at let's look at a partial grid. A partial grid, I mean you have something like this, and then you have this, and maybe also this, and this, and this. Okay. And you want to color this with two colors. Now, if you color it with two colors, there is indeed a boundary. So there is a boundary, which is a path. Everybody here is red, and everybody else is not red or something. But you have to analyze how these paths can be. And it turns out in this case that the linear trick is easy. The lineal trick is easy because the convex colorings, if you join one additional point to everybody else, and you have x plus 1 colors, this is the same as what you did with x colors, and you multiply by x. With the additional point out here, you must get a different color, and then everybody goes. But it turned out, so this we knew. But then you want to know, is there a difficult point? Is there a number of colors for which it is hard? And I had posed this as an open problem at Lova's 60th birthday after spending a whole day talking to Peter Winkler, who is kind of the world record holder in counting complexity and things like this. And we couldn't solve it, and then we decided, I presented at the open problem session, and it's published there as an open problem session. 2 days later, Steve Noble and Andrew Goodall came to see me and said, we solved it. Okay. So they published it in the archive. But indeed, what I said before, they felt that this is not enough for a full paper, but they wanted the credit. And we discussed that maybe if we have more examples, we put it together into another paper, which we finally did. But anyhow, so here is a case where the reduction was easy, but finding a point for which it is hard. In this case, it's already 2. 2 is the point. Was a non-trivial effort, and indeed their proof is 16 pages, so it's not a trivial exercise. Now there is a notion of coloring which exists in the literature for engineering reasons, and there was a paper, and then there is a whole booklet by British combinatorists. And they are called harmonious coloring. So they come somehow together with complete colorings. Now, a complete coloring is a coloring where every pair of colors occurs at as endpoint of some edge. Okay. And the harmonious coloring is where every pair of colors occurs at most once along some edge. Now the first case, complete coloring, is not a polynomial in K. You can verify this for you. So I just mention it because it appears in the same discussion in the literature. But the harmonious colorings happen to be also a polynomial in K. They actually can also be looked at as a Harari coloring, but with a slightly unexpected. So we don't need this. And so let's look what we can say about the complexity in this case. Now the harmonious colorings are well, they have a motivation in engineering. There are plenty of papers doing extremal graph theory about them. And they are interesting because they are the first example of graph parameter, I mean counting the minimum number of colors to be able to do this, or the minimum, which is NP hard on trees. So this is a case where tree width doesn't help you to compute the case. It's a natural problem about graphs, which on tree width 1 is already hard to compute. So actually we came along this first because we had to show something, and we could show that the harmonious colorings are not monadic second order definable, but using the fact that P is different from NP, because then we have this result. And finally we also had a proof that it's not monadic second order definable without a complexity theoretic hypothesis. Anyhow, this is a very good example. So what can we say here about the complexity of evaluating the polynomial? So for every k, the harmonious colorings is easy to compute for k in n, because there are only finitely many graphs without isolated vertices which admit a harmonious coloring with k colors. However, this is not uniform in the sense that for each k, you want to evaluate it for k3, k4, you always get a polynomial time Turing machine, but the machine depends on k, which is not the case for the characteristic polynomial, where it's a determinant, so the polynomial is always degree 3 at most, and you don't care what happens. So here it depends on k. On the other hand, still you have the situation that for every complex number which is not a positive integer or 0, the evaluation is sharply hard. So here you don't have you have a dichotomy, but somehow in a non-uniform way. I mean, the polynomial thing gets harder and harder and harder and harder, and then above a certain level everybody is sharply hard. But it's not. It's not a counterexample, but it's a unexpected behavior. And actually, the trick for the hardness is quite tricky. So first of all, we define a new graph which we call S of G. So you start with a graph G, then on every edge you add a new vertex, you get this as an intermediate graph, and then on all those new vertices you got, you make into a clique. Now this is a graph transformation which is polynomial time computable if you do it as a graph algorithm. And the point here is that this is kind of a unexpectedly tricky form of linear streak. You get that the characteristic polynomial, there is a C missing here, of this new graph of k plus e is the number of edges of the original G, is the same as the original chromatic polynomial of G as k colors times a correcting factor, which it uses both k and e. Okay, so this allows you to show that something is sharply hard because you know this about a chromatic polynomial. It still have to do a bit of work here, but this is the crucial ingredient. So I have here a sketch of the proof which you can read carefully when you look at the slides after I posted them. I don't think it is helpful to read the proof here. Now the next case, so here we are successful now. At least we understand the harmonious case, we understand the convex case. So now we got courageous, and there is a thing which was introduced by Noga-Alon, Ding, Oprovsky, Vertigan, partitioning into graphs with only small components. So here the idea is, instead of every color class consists of edgeless graphs, you say every color class consists of very small connected components. So either a single vertex, or for t equals 2, one edge, or for equals t3, a point, an edge, or a path of length 3. Okay. So this is MCC. There is a reason for calling what monochromatic. I forgot what MCC stands for, but something which uses monochromatic and components and connected, monochromatic connected components of size t. Okay, we got it. And again, counting the number of such colorings for fixed t. Now t is fixed, k is the number of colors, is a polynomial in k, but not in t. So t is fixed. Okay. So here is again a graph. It's not necessarily, or at least it doesn't look like a Harari polynomial. We'll see later a list what looks like Harari polynomials. But here is another graph polynomial. And it seems, at least for t equals 2, this seems to be a minor generalization of the chromatic polynomial. So what can we do about it? So here, actually, we had a rude awakening. For every t in n plus, computing this polynomial for G with 2 colors is sharply hard. And this uses a classical result of Nadia Crenio and Mickey Herman on the complexity of generalized satisfiability counting problems. But we couldn't do better. We failed to see how to use a version of Lineal's trick. Actually, we had one, it turned out to be wrong. I mean, we worked 6 months, we had pages of manuscripts and computations and tricky applications of all kind of stuff, which finally collapsed. When we reread and copied it, finally it collapsed. So this is the best thing we got. But actually for every t, so there should be, yes, for every t, but 2 colors, it is hard. And we, meaning we couldn't do it, we really spent a lot of correspondence and time together. All the authors here couldn't do it. So what is the full complexity spectrum of the MCC colorings? We don't know. It's a really rude awakening. And actually even here we had to work hard to figure out what we got. So then we said, well, let's be modest. The MCC colorings are such that the color class may consist of single points, of single vertices, of paths, of triangles, whatever T is. So, but this is a mixture. So let's look at the disjoint union H colorings, where every color class induces a graph which is a disjoint union of a fixed graph H. And H could be, to start with, an edge. So instead of having a point and an edge, we just said points we understand. If it's only points, we understand. So it only consists of disjoint union of edges. Can we do it then? Okay. So if K is 1, H is K is 1, there's a proper colorings in general. And we know for any H this is a polynomial, because now we are in the case of the Harari polynomials again. And every such coloring with a clique KT is also a MCCCT coloring, but not the other way around. So there we worked hard, and we could prove that for every t, which is a positive integer, evaluating disjoint unions of KTs with 2 colors is sharply complete. So this sounds good, yes, this is already not bad. So for 2, but for every t, we have at least 1 difficult point. And then we also have a reduction, again, which is complicated. I don't want to get into details, but again we have a operator on graphs, which is a box H and B. So you take your graph G, you pick 1 point, so here is my G, you pick 1 point in G, and you connect, how does it go? The edges and...
This vertex is complete G, but anti-complete H.
Yes, anyhow, okay. And then you play with this. Again, I don't want to get into details, but here we managed to do a complete analysis. And so we could go on. So I have shown you cases where we somehow managed to do something. Now here are more colorings for which you can ask yourself. Injective colorings which were introduced in the literature by Hahn, Kratochvil, Sira, and Scotto. I avoid examples which I just pull out of for the sake of pulling out something. So, but injective colorings is where every neighborhood, you have a vertex, and every neighboring vertex has a different color. And path rainbow is an edge coloring where for every 2 points there is a path, where every edge on the path has different color. So all those things, these are also appear in the literature. Or you have, these are again the a slight generalization of the Harari colorings, you can also have, instead of each color class induces a graph in P, you can say each color class induces a graph in P, and the union of two color classes induces a graph in P prime or something. And this still gives you many graph polynomials, and indeed acyclic colorings were introduced like this. And there is a paper, so this is again not a crazy invention of mine, but this was already in '73. Somebody looked at acyclic colorings, and you can do it here also. So again, this gives you many new graph polynomials, and here is a list how you can do those things, just to show you that our notions are not so bad, as if so these are the Harari colorings. All graphs, P1 is all graphs, and P2 is all graphs, so this gives you trivial colorings. Any coloring is fine. If this is edgeless graphs and P2 has no condition, then this gives you the proper colorings. If this is edgeless graphs and P2 is forests, then you get acyclic colorings as before. If you take P1 to be connected graphs, you get the convex colorings we have seen before. Here is the funny thing. Harmonious colorings can be described with two properties like this. You take proper colorings and such that the disjoint union of two color classes contains at most one edge. This gives you the harmonious colorings. MCC colorings can be written like this. Disjoint union H can be written like this. Then there is something called T imperfect colorings, which appears in the literature. There is something called co-colorings, which appears in the literature, and these are the H-free graphs colorings, which appear also in the literature. So there are many cases in the literature which were studied, which still are open for us. And indeed, the H-free colorings have been studied a little bit in the literature. We look at generalized chromatic polynomials with H-free. We have seen before already. For H equals 2, this we have the dichotomy property, and for H equals 3, this counts the triangle-free colorings. And what do we know about those? There are some results by Achlioptas, Brown, Cornell, Molloy, which says that it's Sharpie hard for every k bigger than 3, and h of size at least 2. But again, we don't know about non-integer values. And Achlioptas has shown that the computing is NP hard, not Sharpie hard, NP hard for every h of size at most 2, but he doesn't know Sharpie hard. So it is again a challenging problem. If you want to work on it, characterize H for which H-free coloring satisfies some form of dichotomy. So again, I'm just repeating here, for which cases can we analyze the complexity completely. Now, this is just a summary of what we have done. So for the trivial colorings, we know everything. For the characteristic polynomial, it's always easy. For the generalized matching polynomial, we have it's hard, but this was known. For the chromatic, this is the paradigm. For harmonious coloring, we have a result which is new, and this is non-uniform, as I mentioned. The convex colorings, we also have a result, and for the new colorings, we also have some results, and the rest is wide open. So actually, yes, I mean, although there are many impressive examples where the dichotomy seems to hold, in the case of the univariate polynomials, if you hear, I open you this space of Harari colorings, we know actually very little. So here is also a summary where we have only partial results for the H chromatic polynomial and for the MCC colorings, and for the H-free colorings we only have Partial results. The number refer to the paper which just has been published in the European Journal of Combinatorics. Thank you.